Welcome to Demystifying Math. This is part 4 in a video series on graphing functions that have asymptotes. In this particular video, we're going to be graphing a function that has an asymptote and a hole in the graph. Let's look at the function f of x equals x squared minus 3x all over x squared minus x minus 6. The first thing I'm going to do is factor both numerator and denominator. So in my numerator I have x times x minus 3. In my denominator I have x minus 3 times x plus 2. In its factored form you can identify the domain of the function. This function will be undefined at x equals 3 and x equals negative 2. Of course we could simplify further and cancel out the x minus 3's. And we're just left with x over x plus 2. They are similar functions, except the new function is defined at 3 where the original function was not. So we're going to make a domain restriction on the simplified function so that they are exactly the same graphs. So since we have 2 points at which our function is undefined, we're going to look and see what happens to the graph as we approach those two numbers. Let's start off by looking to see what happens to the function as x approaches negative 2. So we're going to plug in some numbers very close to negative 2. I chose negative 2.1, which was 21, and negative 2.01, my y value is 201, and at negative 2.001, we're up to 2001. So it looks like the limit of the function as x approaches negative 2 from the left side is infinity. Let's look and see what happens as we approach negative 2 from the right side. So we're going to plug in again some numbers very close to negative 2. Negative 1.9 I chose, negative 1.99, and negative 1.999. These output values are heading toward negative infinity. So the graph is going to be unbounded as we approach negative 2, which means that we have a vertical asymptote at x equals negative 2. Okay, we also had an undefined value at 3. Let's see what happens as we approach 3. I chose to put in some numbers really close to 3. 2.9, 2.99, and 2.999 all have output values that are very close to 0.6. So the limit as we approach 3 from the negative side is 0.6. Let's look and see what happens on the other side. At 3.1, 3.01, and 3.001, I also have numbers that are approaching 0.6. So this limit is also 0.6, which means that in general the limit as we approach x approaches 3 of the function is equal to 0.6. Not infinity like we found before. It's actually approaching a specific number. So we would say that we have a hole in our graph at the ordered pair 3 and 0.6. So what we're going to do is draw an open circle at that point to show that it's not part of our graph, but all the numbers right up to 3 and 0.6 are included with our graph. Now we could have gotten a 0.6 pretty easily. If we look at the simplified version of the function, it is defined at 3. So if we plug 3 into that function, we get out the 0.6, which is the missing point on the original function. Okay, so now that we've gotten that taken care of, let's go ahead and look for our horizontal asymptote. We're going to do that by dividing each and every term of our function by x squared and then taking the limit as x goes to infinity. So when we take each one of those and divide it by x squared, we're using x squared because it's the highest degree that we have in our function, numerator and denominator. So you always want to take the highest degree. And that will simplify your function down quite a bit and make it easy for you to take the limit. Now if you have the limit of something like 3 over x, as x goes to infinity or gets to be an extremely large number, the 3 over that number is going to be extremely small, very, very close to 0. So 3 over x is going to head toward 0 as x goes to infinity. and so is 1 over x and negative 6 over x squared. So you end up with 1 minus 0 over 1 minus 0 minus 0, which just gives you 1 over 1, or 1. So in this case, our graph is going to approach y equals 1. So that's going to be our horizontal asymptote. Now we could have also tested for where x goes to negative infinity, but we should get exactly the same answer. Okay, let's see if it crosses its horizontal asymptote. So we're going to do that by setting the function itself equal to 1. I'm going to bring the 1 over to the other side and then find a common denominator. So 1 is the same as x squared minus x minus 6 over itself. And then we're going to bring our two fractions together as 1 and simplify. So you should see that the x squareds canceled out, and I'm left with negative 2x plus 6 in the numerator. Well, the only way that this is going to equal 0 is if the numerator is equal to 0. But let's go ahead and factor this. We're going to factor out the negative 2, and we're left with x minus 3 in the numerator. And we have another factor of x minus 3 in the denominator, which would cancel out. And if we canceled them out, we'd have negative 2 left in our numerator, which can't equal 0. So there's no way this is going to actually equal 0. Even if we had said, oh, well, it's going to be a 3, well, then it's going to end up being undefined because 3 is not part of our domain. So any way that you want to look at it is fine. This one's not going to cross the horizontal asymptote. The only possible number we got for the numerator equals 0 was 3, and it doesn't work for the denominator because it's going to be undefined. Okay, so let's go on, and what we want to do is find out where our graph is increasing or decreasing. And we're going to do this by taking the first derivative, but we're going to take the first derivative of the simplified function. Remember, the two functions are the same everywhere except at x equals 3. So we're just going to keep that in mind as we go through. They should have the same behavior everywhere on the graph. So where one is increasing, the other one should be increasing. Alright, so with the simplified form, it's a lot easier to take the derivative. So the numerator is x, we're going to call that u, and the denominator is x plus 2, we're going to call that b, and then we're going to use our quotient rule. So it's going to be the v u prime minus uv prime in the numerator, all over v squared in the denominator. Okay, so our x's are going to cancel out, and we're left with 2 over x plus 2 all squared. Well, remember that when we're looking for increasing or decreasing, we're looking where the first derivative is positive or negative. In this case, we have a positive in our exponent, and if we square anything, we're going to get a positive, so our denominator is positive. So no matter what numbers we put into this first derivative, we're going to get out a positive. Okay? We could set up our intervals, and in this case my only critical point is that negative 2, so that normally would be the only thing I put there, but I also put the 3 just to remind myself that 3 is not my domain, so I don't want to include it on my intervals when I talk about increasing or decreasing. And in this case, everything is increasing because it doesn't matter what numbers I put in, I'm going to get out a positive number for the first derivative. So we would say that this graph is increasing from negative infinity to negative 2, and again from negative 2 to 3, and from 3 to infinity, or you could say it's increasing everywhere on its domain. Since we don't change from increasing to decreasing or vice versa, there's no turning points. Okay, so now what we want to do is look at the concavity of the graph, and we're going to take the second derivative. I'm going to rewrite my first derivative as 2 times x plus 2 all to the negative 2, just so I can make it a little bit easier to take the derivative, and now all I have to do is use the chain rule. So I'm going to bring the negative 2 in front as a product with the 2, and reduce my exponent by 1. And then I simplified. Now in this case, I have x plus 2 all to the third in the denominator. Since it's a cubic, we could have positives or negatives in the denominator, so this could change signs. My only critical point is at negative 2, but again, I'm putting the 3 on my number line just to remind myself that it's not going to be included as a number on my intervals. Okay, so below negative 2, I chose negative 3. And I got out a 4, which means that it's concave up because it's a positive number on the interval from negative infinity to negative 2. Between -2 and 3 I chose 0 and I got out a negative, which means that it's concave down. Now it should not change concavity beyond 3. Should still be concave down because 3 was not a critical point on our second derivative. But we'll go ahead and check it just to verify. And I chose to put in a 4 and got out another negative, so it is concave down on that interval as well. We just can't include 3 in our intervals because it's not a point on our graph. And in this case we have no inflection points because the only place where it changed concavity was at -2, which is where we have an asymptote, so there's no points there. So we just have concave up from -∞ to -2 and concave down from -2 to 3 and then again from 3 to infinity. Okay, the only other thing we need to do to draw a graph is plot a few points. I chose a few points below our vertical asymptote, or to the left of it rather, and a few points to the right of it. You can plot some other points if you want to. I just chose these. Okay, so now you're going to draw your graph. First of all, you're going to draw your vertical and horizontal asymptotes. Use a dotted line to show that they're not part of your graph. Then you're going to plot the points that you found, as well as the ordered pair of 3.6, at which you're going to put an open circle to show that it's not a point on your graph. On the left side of x equals -2, you're going to draw the curve that's increasing and concave up. And on the other side of x equals -2, you're going to draw a curve that's increasing and concave down. You can pause the video for a few minutes and try to draw your graph and come back and check your work. Okay, so you should have a graph that looks similar to this one. You have a hole in the graph at 3 and 0.6. You have an ordered pair at 0, 0 there. You have the graph heading toward the asymptotes, which are at x equals -2 and y equals 1. On the left side at x equals -2, you have a curve that's increasing and concave up. And on the other side, you have a graph that's increasing and concave down. Alright, thank you for tuning in to Demystifying Math.